So like I said, this one we crossed out. My matrix product is not commutative. We cannot equate freely AB to BA. Under some circumstances, you probably will be able to do that. And it will be very lucky, very favorable circumstances. But in general, you can't. So to present my properties, I'll fix three matrices. And I will discuss the square matrices. Some of the properties can be extended to rectangular matrices, but it depends. Most of the time, we will be looking at the square matrices. So I have three square matrices. I fix a number. Now, a few simple laws, quite expectable, which resemble the numbers a lot. I will give you them first. Associative law, it says when you multiply the matrices, you can do it when you can put the brackets in any way you wish. You can first multiply B and C. While doing so, you will need to do lots of dot products, and then the result you can multiply with A. Again, you will do lots of dot products on that occasion. If you do now in the opposite way, if you do your dot product between A and B first, and then you take the result of this and then you will do the dot products with the bracket and C, that will be the same result. It's not so obvious this time as it is obvious with numbers, even after, especially after the example with the non-commutative example. I mean, yet for the matrices, this one you can expect. So if you multiply A, B, C, it doesn't matter in which order you do that. You can do A, B first, and then the result with C, or the other way around. A, you just leave it alone, B, C first, and then A with the result. As long as you keep the order of the factors, if the leftmost factor A, it should stay leftmost factor. If the B is the C is the rightmost factor, it should stay the right. As long as you're not changing, as long as you're not flipping them around, you can go with this, with any order. Another expectable, rather expectable, like I said, it is expectable property, but it just, the proof, that will require substantial proof, in fact, if you try to establish that, unlike numbers. I think the yellow book has this proof, so if you're wondering how it goes, you can go and check that. The other expectable property for the matrix product is what I call this distributive law. It means that if you multiply a matrix by sum of the other two, as long as everything is compatible, in case when they are square matrices, everything is compatible, you can multiply, you can distribute your factor across the terms of your sum. Again, as long as you keep the order, as long as you're not flipping them around, you're good to go with this identity. So you're not supposed to write something like this in general, because AB is not BA. Now the expectable is the one with scalars. Now, the one which is less expectable, let me just say it again. When I say expectable, of course, I mean they are expectable because they resemble numbers a lot, and we can hope that they are true. But in case of matrices, it will require substantial effort to prove something like this. Now, the one which is less expectable is unity. With numbers, we have this special number, which we call 1. What's the special feature of that number? Distinguished feature. It is that if you multiply any number by 1, does nothing change, right? Do we have anything like that with matrices? Do we have this special distinguished element such that if I multiply the other one by this element, it doesn't change? Well, when we find such an element, we will call it identity matrix. But before we can call it identity, we have to find it, right? How can we find such an element? I mean, I guess the person who said identity matrix, he probably saw it before, but just ask yourself this, how could possibly you find such an element? Of course, you've been shown it, and I saw it in the book. You can say I found it in the book. But the person who didn't have a book, the first one, how did he find that element? And just put yourself in the shoes of this first person. Try to find this element. Can you guess it from your intuition? It's not an easy element, in fact. All ones doesn't work because we don't multiply them So like the logic we use to come up with the zero matrix, it doesn't work here anymore because the multiplication is totally different. Well, you can, if you put yourself in the shoes of that person who first come up with the identity matrix, you will, with some effort, you will be able to come up with the matrix. It's not really a big deal. But the matrix itself, the way it looks, if you've never seen it before, it's quite interesting. Look at this. So I claim that for the matrix multiplication, in case you're looking at the square matrices, there is a special element, and I will be using the capital letter I very often in boldface to denote that element. There will be the whole range of such elements for different sizes, different elements. And that element will possess the property that if I multiply any other matrix, in fact, with this element, that will not alter the matrix. And this time, you see, because my product is non-commutative, I have to just specify both multiplications, left multiplication and right multiplication, just to give you the completeness of the picture. Now, the element itself, look how it looks. It's the element which has zeros surprisingly across most of the entries. And unities, they only come on the diagonal positions. I don't know if you saw it before, you probably you're not excited right now. But first, if you are the first timer, and people who saw it before, remember how you were the first timers. Remember your excitement. It is an exciting example, quite non-trivial. You cannot just simply guess it from the top of your head. You have to spend lots of times with the matrix multiplication before you get this insight and intuition in order to predict such a result. I'll give you an example of why this works. I choose a matrix here. I think that's the matrix which I choose. It's one of the matrices you already copied on Wednesday, 3 times 3. One of the matrices you copied on Wednesday. Here's my identity of size 3. Let's just see why this works. It's not a proof, but it's just a demonstration why this works. Look at this. I claim that if I multiply A with the identity in this particular order, so A will be first factor, I will be the second factor, the result will be the same matrix A. Let's just see that. First element in the product. We know how to compute that. It's a row 1, column 1. So I take the first row in my first factor. I'll take the first column in my second factor. If I dot product these two vectors, look what happens. Only number 5 will crop up. The rest will be vanished. If I go next element, 3, row 1, column 2. So I have to move this box over here. Dot product just gives me 3 out of the vector. Next element, you see how clever the matrix is constructed. The next element is the vector. Dot product gives me number 9. You go second row, that will give you second row here, negative 2. It will be second row, first column. Dot product will cut out negative 1. I think it's a very clever construction. Not only that, if you take the product in the other order, look at this. If you take IA product, then you have to flip my blue boxes around, right? So this element, negative 2, then will be the second column here, second row here, and the first column here. Dot product gives me negative 2 again. You can't deny this is a really beautiful, clever construction. Who could predict that such a complex multiplication, for such a complex multiplication, you can come up with such a beautiful identity?